Alright, so this time we're solving problem 50 from chapter 4, and in the problem it says, you've landed on an unknown planet, Newtonia, and want to know what objects weigh there. When you push a certain tool starting from rest on a frictionless horizontal surface with a 12 Newton force, the tool moves 16 meters in the first 2 seconds. You next observe that if you release the tool from rest at 10 meters above the ground, it takes 2.58 seconds to reach the ground. What does the tool weigh on Newtonia, and what does it weigh on Earth? So from the start, we know we need to break this into x and y components. So for the x, we know that there's a force applied of 12 newtons, a distance of 16 meters, and it takes a time to go that distance of 2 seconds. And then for y, in the y case, we know that we have a distance of 10 meters and a time of 2.58 seconds. So let's start with the x components. So we need to, in order to find the mass, because we know that force is equal to mass times acceleration, and because it's a frictionless surface, there's the only force over here is going to be the force pushing the block. We need to find the acceleration. And there's a couple of equations that we can use that will give us acceleration. And we're going to have to use both of them. The first one is that the velocity is going to be equal to the final velocity is going to be equal to the initial velocity plus the acceleration times time. And the second equation is that the velocity final squared minus velocity initial squared is equal to 2 times the acceleration times distance. So we know that this term goes to 0, as does this term, because its initial velocity is 0. We can then substitute this into this equation for b. So we get a, the acceleration, times the time squared is going to be equal to 2 times the acceleration times x. We then have an a on both sides, so this can be written as a squared t squared is equal to 2ax. We can cancel that one with that. So we then get that the acceleration is equal to 2 times the distance divided by time squared. And so then we plug in our numbers from over here, and we get that that's 2 times 16 divided by 2 squared, and that gives us an acceleration of, so that's our acceleration, and that is equal to 8 meters per second. We can then use this equation using this acceleration to find the mass. So we know that the force is going to be equal to 12 times the mass times our acceleration of 8 meters per second. So the mass is going to be equal to 12 divided by 8, which is then equal to 1.5 kilograms. And that's our mass of the tool. we then need to find the gravity on this new planet. And so over here, we know that the distance in y is going to be equal to the initial velocity in the y direction times the time that it takes, times the time, plus 1/2 the gravity on that planet times time squared. This is 0 because we're dropping it, so it starts at 0 velocity. We know that this is 10 meters. It's equal to 1/2 g times 2.58 squared. So that then becomes g is equal to 10 divided by 2.58 squared times by 2, which gives us a gravitational pull of 3.00 meters per second squared. So we can then find, using the mass and gravity, we can find the weight of the tool. So the weight of the tool on the new planet is going to be equal to the mass times the gravity of the new planet. And that's going to be equal to 1.5 times 3.0, which is equal to 4.5 newtons. And then the weight on Earth of the tool is going to be equal to the mass times the gravity of Earth, which is then 1.5 times 9.81, because that's the gravity on Earth, and that gives us a weight on Earth of 14.7 newtons. So that's the weight on Earth, and that's the weight of the tool on the new planet, and that's how you do that problem.